Hello, class. Okay, so we're going to begin our third section, and we're going to talk about momentum. So first, we're going to define momentum, and then we'll see, what it's good for. So to start out, momentum starts with M, just like a lot of other things. So we give it a different letter. We use a different variable, and for some reason, we use P for momentum. And we define the momentum of an object to simply be its mass times its velocity. And so units, we have kilogram meters per second. Now, we could write this in a different way as well, but these are the basic SI units. If we multiply by a second over a second, here, let's do it this way. A kilogram meter per second squared is a Newton times a second. So that'd be an equivalent way of talking about momentum. Just, whichever is convenient at the time, that's the one you use. Okay, now, historically, when we introduced Newton's laws, he said, law of inertia, F equals ma, and, forces come in pairs. If you ever tried to read Isaac Newton's actual work, good luck with that. It's extremely difficult to read for a couple reasons. One, it's just very difficult stuff, but also the math used is very different. There's a story. There's this really famous physicist, Richard Feynman, who, one of the greatest physicists of the 20th century, top 5 easily. And he wanted to give his students a lecture on planetary orbits. So he went right to the source and got out Newton's book, and he could not follow it. And it's not that he didn't understand it, it's just the math, the way that they used math back then is just very different. Newton only referenced 2 books in his published work. One of them was Elements by Euclid, and the other is, I think, even older than that. And people just don't use those sources anymore. Math nowadays looks fairly different than what Newton was using. But anyways, Newton did not even define his second law, not exactly as force equals mass times acceleration. What he did is he didn't call it momentum by name, but he basically defined momentum, and Newton wrote his own second law, as force is equal to the rate of change of momentum over time. And if we just consider a single particle, this is the exact same thing, really. We have an object with a mass m moving with a velocity v. And if we look at the change in momentum, that would be mass times v final minus mass times v initial over delta t. So we're just considering a particle with a mass m, but its velocity might change. So delta p would be the final momentum minus the initial momentum, and we can factor the m out. And then we have v final minus v initial, which is delta v, and then we divide by delta t, and remember acceleration is a change in velocity over time. Now, of course, when we define acceleration, or these kind of quantities with these, changing rates that appear in fractions, and you take the limit, to give a precise definition, we'd have limits everywhere, where you take the limit that delta t goes to 0. So this is how Newton defined his second law. Force is equal to the change in momentum over time. And again, for a normal particle, it's the exact same thing. Well, it's interesting. We're going to see like momentum is especially useful when we deal with more than just small systems with a few particles. It's great for dealing with larger systems of particles. Like every case we considered before, we'd either have an individual object or two objects that move together. Like if we have, draw it over here, something like in the lab where we have a cart and a hanging mass, and you release it, these two objects move together. If mass 2 falls 10 centimeters, mass 1 is moving 10 centimeters to the right. So they have the same displacement, just different directions, same velocity, same acceleration. But the real world things aren't always that simple. And we're going to see momentum can be extremely useful when we're dealing with systems of particles in particular. Okay, now we're going to find something else. First, we're going to find something called impulse. I mentioned that momentum can be great when dealing with more complicated things. And one thing where momentum is particularly useful is when we deal with collisions. So let's look at a simple example of a collision. Let's say we have like an immovable wall, and say we have like a rubber ball. And we throw it at the wall, so it's going to hit the wall with a certain velocity and then bounce back. And again, it appears to happen almost instantaneously if you're just looking at it visually. The time that it's in contact with the wall is just a fraction of a second. And so if we were to plot the force that the wall exerts on the ball as a function of time, now the force would be to the left in this case. We're looking at the force that the wall is exerting on the ball. So really it should be negative, but let's just plot the magnitude of the force. And yeah, it's going to be 0 until the collision happens, until the ball hits the wall. And then the force is going to quickly rise because the ball is somewhat elastic. It's going to, compress when it hits the wall. Interestingly, even things like baseballs and golf balls do that. If you hit a ball like a baseball with a bat, they've done photographs where you get it just frame by frame, and you can see when the collision occurs, that ball gets smashed into something that clearly is not spherical. So they seem very rigid. And so we're dealing with a non-constant force, for one thing. The force, like right when there's initial contact, and then force reaches some peak value, and then goes back to 0. And if you look at the time where it's not 0, let's call that delta t. Delta t is usually a very short time interval, like a fraction of a second. Okay, and so what we're going to do is we're going to find something called impulse. And yeah, I think the word, or the letter I is used for other things in physics. So we use the letter J for impulse. And what we're going to do is we're going to find this as the area under the force time curve. So impulse is equal to the area. So like in this particular case, let's say that this is what the force looked like. And we define the impulse as the area underneath that curve. Now let's talk about the units of impulse. So, we're multiplying a force times a distance to get the area. So the units of impulse are Newton seconds. And remember earlier when we were talking about units, a kilogram meter per second is equal to a Newton times a second. So they have the same units. Okay. Now, calculating the impulse might be challenging for two reasons. For one, how do you find the area under a curve? It's kind of a complicated thing. Well, I mean, I guess depending on your perspective, but for us, we can't do it unless it's a nice geometric shape. But the real challenge, though, is just knowing what this curve actually looks like. Like, how do you know what this looks like? Like, if you were to throw a golf ball at a wall, how are you going to figure out what this looks like in the first place? And so what we're going to do is we don't really care about the detailed description of how the force varies with time. Really, the impulse is enough. And so what we're going to do is we're going to find an equivalent area. And I'm going to start out by drawing a rectangle. I'll use a different color. Now let's look at the area underneath that rectangle, and how does it compare to the actual impulse in this case? And clearly, this is much smaller. Like, the area under this rectangle is much smaller than the area underneath this curve. Well, what if I make a much bigger rectangle? Because we can use a different color again. So again, the width is equal to delta t. What if I make this rectangle? Well, clearly the green rectangle has a much greater area under it than... So let's look at it this way. We have green is greater than black, which is greater than purple. I don't know why. Guess it wasn't really necessary to change colors in writing this here. But, what do we care? Well, point is, let's say we take this purple rectangle and we just raise the height and just keep raising it. Eventually we'll get to the area of this, under this purple rectangle. If we raise it all the way up to this green level, then the area is going to be bigger, but it's just going to gradually increase. And so there has to be some level, maybe right around here. If we draw this rectangle, there's got to be some point between purple and green where the area underneath that rectangle is equal to the area underneath the curve itself. If you start here and keep raising it, the area keeps increasing. Eventually, you're going to hit the right area. And so we're going to use this to define what we call the average force. So we define the average force so that if we just calculate F delta T, or F average delta T, that is equal to the impulse. Okay, so, and again, we usually don't care what the details are, like how the force varies with time. What we usually just want to know is the total impulse, because that's what's going to have a noticeable effect. Like, the impulse is going to cause the motion of this ball to change, and it doesn't matter if it happened, if the force increased and then decreased over a fraction of a second, or if it was a constant average force over that whole time interval, the end result is going to be the same. So, we use this to define the average force. So let me erase this. I'm going to start collecting equations. We have momentum is mass times velocity. And impulse is area under FT curve, with units newtons times seconds. And again, those two units are the same. So now we can get rid of some of this. Okay, so our, and we can see our, basically the result is our impulse is equal to the average force times delta t, and the average force would be the mass times the acceleration, which I'm going to write this way. And then we can cancel out the delta t. And remember, this is just equal to the change in momentum. This would be mass times v final minus mass times v initial. This would be p final minus p initial. And so the impulse is equal to the change in momentum. So basically, we've just defined a few things for now. But yeah, we're going to get to a very important application soon. So I mentioned earlier that momentum is very useful when we're talking about systems of particles. And we define the momentum for an object, just a mass. Its momentum is mass times velocity. What if you, and I should point out, momentum is a vector. So we could write it this way. It should be obvious that it's a vector because velocity is a vector, so and we're multiplying by a scalar, that gives us another vector. Usually, we're going to stick to one dimension in most cases. Although, towards the end of this chapter, we'll also look at 2 dimensions. But for now, let's just stick with 1 dimension. So, let's say we have, say, mass 1 moving with a velocity v1, and mass 2 moving with a velocity v2. And so we can say the momentum of mass 1 is p1, and momentum of mass 2 is p2. And we define the moment, if we define our system to be these 2 masses, then we use a capital P to define the momentum of the system. So capital P is the momentum of the system. That'd be P1 plus P2 in this case, but in general, you know, if you have 10 masses, then you just find the momentum of each one, add them up, that's the momentum of the system. Now, when I'm just writing on the board, it's kind of hard to tell that this is capital, these are lowercase. So for capital P, I just put that little line underneath it. So again, yeah, these are all vectors. And so the momentum of a system so uppercase P is the momentum of the system, and that's equal to the sum of the individual momentum of each part of the system. And again, drawing arrows above everything, but for now we're sticking to 1 dimension where the plus or minus sign is all we need. Okay, so let's, we can also talk, now that we have our system, let's look at this system in particular. What forces acting on this system? Well, they've got normal force. We'll call that Fn1. Here we have m1g. We have gravity here. Now, there could be friction as well. And I want to erase these. because those are not forces. So let's just say like V1 and V2 like this. Okay. Now, generally there could be friction, but we're going to ignore that for now. So we put wheels on it, friction is insignificant. And so we can talk about the net force on the system. Let's not bother with arrows, even though everything's a vector here. So the net force on the system, we have Fn1. You know what, maybe we should. Because they're pointing in opposite directions. So in this example, the net force on the system right now would be equal to this. However, let's say V1 is greater than V2. So eventually this mass is going to smack into the other one. And when that happens, they're going to exert forces on each other. So at least over a certain time interval, these two, there's going to be these forces due to these are forces due to the collision. So F12 would be the force on mass 1 due to mass 2. And again, this would be a very short acting force. Because, if they collide and bounce off each other, these forces will only act when they're in contact typically. And something very important happens here when we look at this, this example. First off, we have 6 forces that are acting on our system. And we want to define them, we want to give them names, or we want to distinguish between the 2 types that we're dealing with here. So I have to explain what that means. But the normal force, I'm just going to write it down and then explain it. We're going to call these external forces. And these forces are internal. Okay, now if we're going to give them names, there has to be some reason for it. There's got to be something significant that is different between these 2 forces, and there is. There's something very important here. And, well, in this particular case, if we look at the external forces, what is the sum of the external forces? And the answer happens to be 0 in this case. Why is it 0? Well, the normal force just balances out gravity. Here, this normal force balances out gravity for this one. And so these are going to end up to be 0, but that does not have to be the case. If we give this an incline, instead of having like a level ground, like say this was the cart we use in lab, and even give it a slight elevation, or slight slope, so change in elevation, then gravity and the normal force would not cancel each other out. So these do not have to be 0. However, the internal forces are always going to be 0. Oh yeah, so what is the defining characteristic between internal and external? Well, let's look at the normal force, both of them. Where do they come from? So just to be clear, our system consists of mass 1 and mass 2. So basically, we can say the universe overall consists of our system, mass 1 and mass 2, and everything else, whatever is not the system is just the rest of the universe. So anything that is not these 2 masses is, not part of our system. So anyways, the normal force, we have to ask, where does this come from? And it comes from the ground. The ground is not part of our system. Therefore, the normal force is an external force. Where does gravity come from? It comes from the Earth. The Earth is not part of our system, so that's external. Same with these. Now let's look at F12. That's a force on mass 1 due to mass 2. Where is this force coming from? It's coming from mass 2, which is part of our system, so we call that an internal force. And F21 is coming from mass 1. That's also an internal force. So again, all these forces are acting on the system, but the question is, where do they come from? If they come from outside the system, those are external forces. So out of these, F12 and F21 are internal. Now, why do we care with this distinction between where they come from? Well, the point is, the sum of all the internal forces is always going to be equal to 0. And the reason why is Newton's third law. So like here we have mass 1 exerts a force on mass 2. Mass 2 is going to exert a force on mass 1. And those are always going to be equal in magnitude but opposite in direction. So if you add them up, they're going to perfectly cancel each other out. And so we can make this distinction that the net force acting on a system is equal to the net external force acting on the system. So what that means is you can ignore all the internal forces when we're dealing with systems. And now when I say we can ignore them, what's going to happen when they have a collision, they're not going to change the total force acting on the system. They will change the force acting on each of these masses, and it'll affect the motion of these masses, but overall the net force on the system will not be affected by the collision. And that's a very important point. I think I just want to talk about one more thing here. Yeah, let's look at a more general example where our system just has an arbitrary number of particles. So we can talk about the momentum of our system. Where we just have momentum of each individual particle added up. And again, we can put arrows over this. That won't change anything, but just to avoid writing it. Now, in general, let's say this is at time t1. If we look at some time delta t later, the momentum could very well be different. So let's call that P prime. And if we subtract these, we get the change in momentum of the system. So the change in momentum, that'd be P prime minus P. So we can do this in any order we want. We can say P1 prime minus P1 or delta P1. And then similarly, delta P2, delta P3, and so on. All right. And then let's divide by the time interval, delta T. So this is after time. So let's actually divide both sides of the equation. Okay. Now, what we have here, this is the momentum of the system. And so, yeah, like how the momentum of the system is changing with time. And remember, I think I wrote it, I should have written it over here. I'll just write it, as one of the first things we talked about. So I'll write that on the top. So on an individual particle, the force acting on that particle is equal to the change in the momentum of that particle over time. So what we have here is delta P1 over delta T. That would be the force acting on particle 1. And this next term is the force acting on particle 2, and then the force acting on particle 3. And so if you add this up, what we're getting, we have a force acting on each part of the system. So if we add this up, we get this result that the net force acting on the system is equal to the change in the momentum of the system over time. And again, so basically that's what we got just from how we define the momentum of a system, and then applying Newton's second law to each part of the system, we get the net force acting on the system. Now the system could be very large. Could be, say, like the air in this room. There's more particles than you could ever count in your lifetime. And sometimes these molecules that make up the air collide with each other, but when we're talking about systems, those collisions don't have any effect. And so remember, when we look at the left side, the net force acting on the system, that is not affected by internal forces, things like collisions. And so, we can replace that. Yeah, I guess I'll just erase this. Write it like this. So, the net external force acting on a system. So, that's all you need to know. We can, when we're dealing with systems, we can completely ignore internal forces. And that turns out to be extremely important. These internal forces canceling out based on Newton's third law. But we're going to get to that in another video. What we're going to talk about next is collisions. So, when two objects collide, there's internal forces acting, but those cancel each other out by Newton's third law. I think we'll stop this one here, and then the next video is going to be on collisions.